Hello, everyone. Thank you for joining us, and welcome to today's joint webinar between L3Harris and Teledyne Brown Engineering. Today's webinar's focus is benefits and applications of hyperspectral imagery from the space station. Some notices before we start. I've muted the phone lines for all attendees, so if you have any questions at any point during the webinar, feel free to enter them into the questions chat box, and we'll try to answer as many as we can at the end of the presentation. We are recording this webinar, and we'll have it up on our website at harrisgeospatial.com in the next couple of days. We'll also email you all a link to the recording as well as the slide deck, which you are welcome to share with your colleagues. So my name is Megan Gallagher, and I am a solutions engineer with L3Harris Geospatial. And today I am joined by our main presenter, Amanda O'Connor. Amanda, would you like to introduce yourself?
Thank you so much, Megan. Hi, I'm Amanda O'Connor. I'm the Director of Geospatial Solutions at Teledyne Brown Engineering. Many of you may know me from my time at Harris. I was here for about 15 years working with the ENVI software, but I changed positions recently and supporting the DESIS hyperspectral mission. So I'm really excited to be back with my colleagues at Harris and talk through some of the advantages and value of working with DESIS and also working in conjunction with ENVI. Thank you.
Thank you. So a quick overview so we can get to the stuff that you guys are really interested in. First, we're going to be going over the value and a bit of background on hyperspectral imagery. After that, we'll be going over the DESIS 30 specs and collecting data on the International Space Station. After that's the coolest part, in my opinion. We're going to be going over a bunch of different case studies with the ENVI analytics. After that, we'll be finishing with going over DESIS access, and if we have time, we will also be doing a Q&A session. So we are going to have some interactive poll questions during this webinar, and the first one has just popped up on your screen. And it's, have you used hyperspectral imagery before? You can choose a yes or a no. And with that, we're going to stop the poll. We've got a pretty decent mix of people who have used hyperspectral imagery before and people who have not. So I'm really excited to share this webinar with you guys. If you haven't used hyperspectral before, we will be doing a brief background on why it's such an amazing tool set and the imagery can be used in so many different use cases. And if you have used it before, well, you're about to see some pretty amazing things. So let's do a little bit of background on hyperspectral imagery. This capability has been around for many years, but the compute power and just the kind of systems that were needed to run it have struggled with the large size of the data that has been necessary. And recently, this has been overcome with a lot of different onboard processing, just a lot of advances we've had in all different kinds of technology. Hyperspectral imagery usually has at least 30 different bands as compared to multispectral, and each band is usually around 10 nanometers or less in a lot of cases, so you get very unique, very precise pixels. So whereas a multispectral image, such as a Landsat image, can give you a class like iron-bearing minerals, hyperspectral imagery can give you the exact type of mineral. So if you're having trouble visualizing it, think of it like this. You have an image and you zoom all the way out. You're able to see a lot of blurry shapes and things. Like you're pretty sure that's a house, you can see a road, there are some bushes, but you aren't able to get a lot of unique information that would help you go beyond that. Now, once you've zoomed back into the image, every single pixel is unique and defined. You can now see things like the address on the side of the mailbox or what kind of flowers are growing on the bushes. Because each one of those pixels is so unique, you can pull out that information. That's how hyperspectral imagery works. If each of the bands is so discrete and unique, we're able to pick out these significant characteristics that otherwise we wouldn't be able to see. So for more of a view instead of an analogy, it works sort of like this. On the right-hand side of the screen, we have a bunch of charts on the top. The one on the left is showing a panchromatic image. Panchromatic images are usually higher resolution, so we're able to see more spatial features, but we get less wavelength information. As you can see, they're just sort of a flat line. To the right of that is a normal multispectral image. These usually have lower resolution than panchromatic, but they make up for that with a lot more wavelength information. So we can see things such as colors and get information that can be used for classification and looking at different kinds of spectra techniques. And on the far right of that, we have a hyperspectral image. And that has a great amount of unique information that we can pull out from interactions with all different parts of the spectrum. And it used to have, to make up for this amazing capability, lower resolution or much more expensive sensors, But that's not the case anymore, and that'll be a really cool thing we're going to be seeing in a little bit. So after that background, I hope I've already convinced you why hyperspectral is so cool, but if I haven't, here's some amazing use case and examples to get you thinking about it. You can get a lot more accurate land cover analysis. So going from things such as knowing if it's a field, you can actually do detection of different kinds of vegetation, different types of trees, different grasses, etc., with the spectra. You can do sub-pixel analysis, so you can find fractional components of what actually makes up a pixel, such as if half of it's water, half of it's trees, different kinds of trees, etc. You can get more information about the vegetation conditions themselves, and such as pigment analysis or even chemical interactions for agricultural analysis. And you can discriminate things that look similar to our eyes, but are very different when you're not just looking at red, green, and blue, such as camo versus vegetation. You can do water quality analysis, so looking at algal blooms, nitrogen runoff, etc., being able to pick that in the water itself. And on the opposite side, you can also do things such as atmospheric constituent analysis, so looking at smoke, haze, and sulfuric dioxide in the atmosphere. A really cool example we're going to be going over today as well is picking up marine debris in the ocean, so things like plastic. And another one is looking at oil spills, so you can actually possibly pick up the thickness and potentially the type. So with that, we are going to jump into our next poll question, which is, what other types of imagery do you use? LiDAR, SAR, high-resolution commercial satellite imagery, medium-resolution imagery, or imagery from aerial or drones? All right, we'll give it a couple more seconds. And there we go. We've got a really good mix. A lot of LiDAR. We've got a lot of commercial satellites at high and medium resolution and aerial. And I do have to say I'm very happy about that percentage of SAR in there as well. Just a personal thing here. All right. And thank you for your answers. And I'm now going to pass it over to Amanda.
All righty. Well, thanks so much for that great introduction, Megan. It's definitely threading a needle to talk about hyperspectral at a high level. You either can talk about it and explain the big picture of it, or you're in a 3-day course. There's kind of not an in-between. Great job in condensing that information. So what I'm going to talk about today is really the DSIS sensor, which is a sensor that's on the International Space Station. And DSIS stands for the DLR, Earth Sensing Imaging Spectrometer. These are some images that we've collected across the world with DSIS in equatorial zones, which are notoriously difficult to get cloud-free images. So I'll go into that in a little bit, but let's get into additional information about MUSES and DSIS. So I'll explain some acronyms in a moment, but I want to bring this up to a high level and talk about the fact that these are on the International Space Station. DSIS is not a free flyer satellite. It is located on the ISS Express Logistics Carrier, and you can see from the aerial where that is on the system. Essentially, this is like a flying manned scientific vessel, which is absolutely crazy to me. And Teledyne Brown has been involved with the ISS in many levels, from the scientific glove boxes inside to contracts for other scientific capabilities within the instrument. So we'll go on to talking a little bit about MUSES. MUSES is the platform that attaches DSIS to the ISS. So we need to just get a little bit of nomenclature down to talk about our case study, so you understand some of the benefits and logistics of working with the ISS as an imaging platform. So as you see there, MUSES stands for the Multi-User System for Earth Sensing. And basically, this is the platform that the DSIS sensor is mounted on externally on the ISS. The key things in my mind as an imagery user for this system is its pointability. So it can image off nadir. It has a large capacity for data downlink. It has the ability to install up to 4 robotically, 4 instruments. Currently, the DSIS sensor is taking a slot on the MUSES platform. So we have 3 open spaces. You do have an onboard data processing option. We have a Linux server there, so you could put the NV software there for onboard stowage to downlink data quickly. And one of the big things is the fact that it's inertially stabilized, and you might be wondering why we've got a dancing chicken in the bottom of the left side of the screen. And that's really to illustrate that the ISS is a manned space vehicle, and astronauts need to exercise. There's movement around. So you're going to have vibrations, perhaps if they're on the treadmill or moving about the station. And so with these muses being inertially stabilized, you can see as the chicken head doesn't move and the body is moving, that's kind of that concept of being stabilized and being able to collect imagery despite what's going on board the ISS. One of the other things that's, I think, valuable for people to hear about the Muses platform relative to a free flyer is it can take about 6 to 12 months from an agreement to installation. The ISS National Lab actually covers the cost for sending your sensor to the space station. It goes up in soft stowage on a SpaceX, and it can be installed very efficiently, and the costs are much, much lower. So at the moment, we're talking with others about potentially having complementary shortwave infrared sensors on there, other sensors for laser communications. The other payloads that could potentially fill the remaining bay on Muses is actually quite exciting to me because it could be potentially complementary data to the DCIS instrument. So if you want more information on Muses, certainly let me know, and we can provide some more detail there. But I wanted to give you some background on how we're actually doing this on board the space station. So now on to what people probably really want to know, which is about the DCIS hyperspectral instrument and the specs that really make it what it is. So the ground sampling distance, or pixel size, is roughly 30 meters at the 400-kilometer ISS altitude. Ground swath, the tiles are 30 kilometers by 30 kilometers, but you can have potentially a long swath of those. So you can have, you'll see on another image, some of the longer collects, so it's multiple tiles in a row. The spectral range is 400 nanometers to 1,000 nanometers, and it's measured nominally at 2.55 nanometers. Quantization is 12-bit, and the data are delivered as L1B or L1C, so basically a compressed radiometric image. What really, in my mind, has distinguished DCIS from other sensors that have been in the space in the hyperspectral world is the signal-to-noise ratio. So the 205 to 1 signal-to-noise ratio at 2.5 nanometers has really allowed us to see very distinct features spectrally. That's a very high signal-to-noise for an instrument in space, and we worked very hard with the DLR and Teledyne to achieve those kinds of numbers. Just a little bit more about the pointing. It can point along track and across track. And I'll give you a link for calibration. We went through an extensive calibration effort with the DLR, Teledyne Brown, and an organization called I2R. Basically, DCIS falls in line with your current NASA Earth science imaging systems like Landsat, as well as the ESA system, Sentinel-2. We use the RadCalNet sites. So I would say that the calibration on DCIS is exquisite in my mind, as well as some of the cleanup that we've done with striping that sometimes you might see with a push broom sensor. So all in all, this is a highly robust system that is imaging on board the ISS. So Earth observation from the ISS, why it works and what challenges we have. So as I mentioned, this is not a polar orbiting satellite with a 90-degree inclination that's going to have a specific repeat cycle. We're in a slightly more equatorial orbit that covers 90% of the populated Earth and happily 100% of the tropics. And that means that we can frequently revisit sites that are prone cloud or known cloud cover areas. What this also means is because we're on a manned system, we can potentially upgrade, repair, exchange instruments as the technologies or markets evolve. The traditional barriers to get to space are minimized, as I mentioned, with the Muses system and the cooperation with the ISS National Lab. Basically, you're working with something that it behaves quite differently, and that can sometimes be startling. I came from a very polar orbiting centric world, and I had to learn a few things, and that's what I've got here in the challenges, as you are in a manned space system, so you do have to do maneuvers to maintain your orbit. There are resupply missions. Imaging doesn't happen on those days. Spacecraft location can cause miscollects, such as what we call a high beta angle, where it's sitting in a position where it's illuminated by the sun. And that can cause issues if you're doing field mission and you're trying to collect data alongside that. if there is a spacewalk or something like that, we have to cancel imaging for that day. So we try to work very closely with people to ensure they get what they need, but it's a different way of thinking of imaging from space. And with the equatorial orbit, the highest we can get is 55 degrees north, and the lowest we can go is 51 degrees south. But overall, we're covering a vast majority of the Earth's surface, and it's proved to be quite sufficient for many of our users. So let's talk about some of the imaging opportunities on the ISS. As I mentioned, there's not necessarily a specific repeat cycle. The ISS does, one thing I forgot to mention in the maneuvers part, there's been times when we're like, is it flying backwards? Did it turn over just now? So we see some strange things. It is a laboratory, but this is typically what we predict for the imaging opportunities on board the ISS. And take note on a couple things on this slide. So basically we have cities across the world arranged from north to south. We have the weeks across the bottom. I know that's fine print, you won't be able to read it, but the takeaways here are, obviously you can get to Canada pretty frequently in the summertime. But in the wintertime, the sun angle is probably going to be too low, and our ability to collect in that area is not going to be available. In the center latitudes here, you can see that we have much more frequent opportunities for collection throughout the year. So again, cloud-covered areas have more of an opportunity to be imaged. And then you see the same effect in the southern hemisphere when you have a low sun angle. So now we'll get into our third and final poll question. And if you don't see your specific area of interest, certainly let us know, because we'd like to know how you're thinking about working with data sets. DSIS has acquired quite a catalog. We have 200 million square kilometers as of yesterday. So from a big data perspective, what's most important to you? Is it frequent coverage of one area to study change over time? Is it access to a broad data catalog for modeling or deep learning? Or is it ease of fusion with multiple data sources? So think other polar orbiting instruments, drones, other different data modalities like LiDAR or SAR. And it looks like frequent coverage of one area of study over time. So basically change detection came out on front, but the other two weren't too far behind. And I would say that validates a lot of the conversations I've had with people wanting to access DSIS. They do have certain areas that are typically passionate to their heart from either grad school or studies over time. But then we do have people who are taking advantage of Amazon Compute or other large compute platforms to do modeling of data and create deep learning models and applications. And then fusion is always going to be something that it can be really challenging, but it can be really important for making discoveries or complementing certain data sets. So thank you very much for that. So now we will get on to the fun stuff, the case studies. So the image that you're seeing behind you there is a principal component of the Ivanpah Playa and Mountain Pass area. We'll talk about that a little bit more when we get into rare earth elements. So just a little bit of background on ENVI and Hyperspectral. So as I mentioned, I started using ENVI in 1998 when I was at CU. ENVI was developed at the University of Colorado using the IDL software because it was very efficient for working with imagery. And as I said, 8 gigabytes at that time was considered, a big hard drive. So how are you going to work with these, basically 200 by 224 by 500 pixel data cubes in an efficient way in the compute system that was available in the late 1990s? And that's really where ENVI came in. It was designed to work with the hyperspectral data quickly and efficiently and create results without having to wait for days. You might have to wait overnight at that point, but at this point, things that took me overnight in the past take about 2 minutes these days, which is absolutely phenomenal. And one of the other main things is ENVI has curated a large number of hyperspectral tools specific for working with hyperspectral data. And these include pre-processing tools like radiometric correction or radiometric calibration, atmospheric correction. I forgot to mention some ortho correction there. One of the main drivers, one of the main purposes for the hyperspectral tools that are in ENVI for pre-processing is careful pixel care. With hyperspectral, because the signal, you have so many bands, you want to preserve it. You don't want to muddy it. You don't want to have it mixed with other signatures if you're trying to find the needle in the haystack. And that's what hyperspectral has always been very good at. And Envy has very distinct ways for helping you do that throughout your workflow. And if you're interested in learning more about that and how to best work with the data, we'll probably address that at the end with some training options. So here's a little bit more on some of the Envy and hyperspectral tools. So Envy possesses several spectral libraries. And these come from JPL, USGS, Johns Hopkins Applied Physics Lab, from various spectrometers like ASD or Nicolet. These can be used for spectral mapping, but you have probably the best collection of spectral libraries in Envy as you'll find anywhere, and we're always trying to add in more of these. The right side of your screen, you see a number of words, and those words are various indices that Envy has for extracting certain parameters from hyperspectral or even multispectral imagery. So it can look at pigments, leaf area index, soil moisture. I think it's over 60, and they're all well documented with the equations and the online documentation system. They can all be automated. It's just an incredibly powerful tool to take 235 bands down to one band very quickly and efficiently. And here's an example of the automated workflows with the Envy modeler. So this is a visual programming interface that allows people who perhaps don't want to necessarily get into programming or scripting to be able to create an automated workflow that they can then deploy either on a desktop or a server to automatically get information. And as you heard on the sides of the DSIS data catalog, the more imagery we get, the more these automated workflows become incredibly valuable for being able to create answers quickly and deliver information to people in a condensed way. It's not that you're throwing a whole data cube at them, but you're throwing an answer. You're giving them the answer that they need. So let's start into some of the case studies. This first one is really near and dear to my heart. One of the things I first started working on after arriving at Teledyne was looking at what could possibly be done with the DSIS data. And I thought back to a project that we actually did with NOAA. This was back in, I think, 2011. It was the Fukushima earthquake, and there was a large amount of marine debris arriving on the western seacoast. And at that point, we were using WorldView 2 to try to, we would try to model where we thought the debris would be. We would try to collect WorldView 2 data and see if we could find anomalous signatures. So I took that approach generally with the DSIS data. But just to back up a little bit, so marine debris is obviously a major ecological hazard. It can be a transport hazard depending on the size of it. And the images I've seen from these gyres in the ocean with marine debris, nets, and plastics certainly foul up a ship if it's not paying attention to where it's going. There's a significant impact to the marine food chain as well as the seafood that is appearing on your plate. So DSIS can image very remote areas. So you can see here, this is Hawaii, and here's California. And here are some images we collected July 9th in 2019. And here's a mosaic of those images, those four. Basically, I kind of like to say, pointed with a potato. I took a latitude and longitude from the Great Garbage Patch, not even using a decimal, like, 120 and 40 degrees. I mean, it was just like, I'm never going to find anything here. Sure enough, we found some things. We need to do some further investigation, but we believe, given on the position and the possibilities of what else it could be, that we are finding large rafts of debris. And we've also learned that different times of year, different kinds of debris appear at different places. Every week we learn more about these activities and what is possible. So it's really moved into something that I think we have a good opportunity of finding a way to use DSIS to potentially find areas of more dense marine debris so that there's perhaps a better opportunity for mitigation, for at least flagging it on charts. Some of these nets actually have a GPS on them, so if we can get a signature from them, we can track them. We can hopefully build a spectral library to find other types of debris. So there's a lot of options that we have, and we've just begun to scratch the surface. But the process for working through this in Envy was I prepared the DSIS imagery. In this case, I just did a radiometric calibration because sometimes an atmospheric correction over water vapor is constituent of the atmosphere. If you're doing an atmospheric correction over water, you can sometimes remove some of the signals that you're trying to observe. So I usually err on the cautious side of just radiometrically correcting those types of scenes, but I'm open to suggestion. I then used NV's tools to mosaic the 4 tiles together and then ran the Reed-Dial-Lee anomaly detection over that large area to find pixels that look different. I mean, this, in theory, there should be water, clouds, there might be some whitecaps, and there might be some cloud fringe. But if you go with that assumption, there shouldn't be large brown things that have a very different signature from the others. So you can see here in the upper right corner, this is the pixel signature for clouds. This is the signature for debris. And what I'm seeing here is, and what I've talked to some colleagues, this wider absorption feature near this water feature, which would make it kind of difficult to detect in other scenarios, is what we are thinking is the actual debris. And then you have the water signature on the bottom. That can be a little hard to see there. So then, after looking at these pixels and taking the debris, I made a spectral library out of it and used our spectral angle mapper classification to separate the anomalies, like the cloud fringe came up as anomalous because it's not that frequent throughout the image. It's only in certain clouds that you actually have this blending of water and clouds, and it makes a different signature. And then the other debris or plastics, as we're calling them. So, and you can see here the mapping results on the bottom. Some of these maps were multiple pixels in size. And again, this is 30-meter pixels. So you can envision how large these rafts of plastics, they aggregate together through the process of being, churned around in the ocean. In the future, this workflow could potentially be fully automated. We're working in conjunction with NOAA to potentially predict where we would think some of these gyres could occur, and also look at potential point sources of where all of this debris, whether it's fishing debris or plastics or other trash, are coming from, so that you can mitigate it at the source. The Panama Canal would be like a source for this type of thing. So we're asking a lot of questions right now about what is possible, what can we tip and cue, how can we mitigate, and how can we stop this problem. I think that there's a large opportunity, especially with the spectral signatures being so unique with DESIS and being able to collect geometrically accurately in remote places, and also, again, cloudy places that give us a good opportunity of potentially getting a little bit better handle on this problem. So oil slicks and seeps. One area I started looking at was the Mississippi Canyon seep. And NOAA has a very exhaustive report. The New York Times did a study or a write-up on this. And basically, after Hurricane Ivan, there was a leak in a pipeline that was near the BP oil well. And there was some confusion on whether that was part of the BP spill or was that something else. And ultimately, there was a pipeline seeping from the bottom of the ocean near the Mississippi River Delta, the Gulf, sorry. And you can see there, it's a little bit difficult in the red circles, but those are essentially oil seeps. And you can see here, oil on the surface, because of the bubbles, it reflects strongly in the infrared. Infrared is in the red channel in this image, and so you see kind of a red pattern there. You can see where this is in the Gulf of Mexico, and this is where the deepest images are. And with hyperspectral data, there's actually been some really good studies, some of them associated with the BP oil spill, on looking at the thicknesses of the oil, being able to distinguish different thicknesses, condition of deterioration of the oil as dispersants were applied by the USGS at that time. So this is about some of the spectral properties that I used to map the oil extents. And this is a very simple tool to use in NV. It's a scatter plot. So essentially, I'm able to use these two bars along the bottom and the side to compare two bands to one another to try to find something that those two bands have different from one another. So it stands out. In this case, I was able to find these two bands that oil reflected brightly in both of them, but the rest of the scene, as you can see, water reflects typically very dark. You can see some of the efforts to control it here. But encircling that area on that scatter plot, that maps the pixels on the scene, and then I have effectively a map of where my oil spill is. So let's say we were collecting imagery every week or so in that area, we could see how that oil spill evolved and changed with this type of information. Going into water quality, so as we talked about, ENVI provides over 60 plus spectral indices, and several of these are applicable for water quality and looking at chlorophyll absorption, nitrogen, phosphorus runoff, and can really highlight areas. This is Lake Erie. You can see this algal bloom. And a number of years back, there was a harmful algal bloom in Lake Erie. And when I say harmful, it was really harmful, like dogs would drink it and potentially die. So it really contaminated the water supply of Lake Erie. And being able to map the harmful algal bloom signature, there are a number of scientists who have used hyperspectral microscopes to try to understand the signature of these blooms before they become too bad and potentially apply mitigation or warnings earlier on in the process. And so with the DSIS data, we're looking at potential applications for improved water quality analysis, early warning of harmful algal blooms. And again, these processes can be automated through the modeler or the ENVI task, which is more of a scripting language, to create results like this with little to no human input. And these workflows can also be run either inside of ArcGIS or the results consumed inside of ArcGIS. So if you're a land manager or water manager, this type of information can be combined with your GIS, and that adds another layer of value where taking some very complex imagery and combining it with GIS data. This is another one of my favorite applications, archaeology, and it's one of those where you're just like, I would not have thought of that. So this image here is of Belize City in Belize. Essentially, in dry times, vegetation can behave differently in these regions, and that can potentially reveal the presence of ancient structures. So you can think of finding ancient Maya features within these types of images where a community would have settled near the shoreline for water, fishing, transportation access. You've got a scientist doing some ongoing research with DSIS data. Again, we have more opportunities for cloud-free images, and that gives us a much better chance of getting some solutions. We've done some co-collects with them to try to do some field work with collecting ASD signatures of the plants to show the different conditions and potential correlation with archaeological finds. This is another area where fusion is important because LiDAR can penetrate deep canopy foliage and potentially find these structures, and then maybe you think you're onto something, and then you get hyperspectral imagery and use that to potentially confirm what you're seeing or enhance what you're seeing so that you have a different level of certainty. And just another comment here, again, because of ISS's activities, if you are doing field work, we want to work with you to try to coordinate and make sure we can collect on the same day. And the best way to do that is work with me in our Teledyne Operations Center in Huntsville. So oil and gas. So the images here are of Bagra in Iraq, or outside of Bagra in Iraq. And we're observing oil and gas flaring. So these types of observations can be used for determining whether wells are in active operation, what kind of active operation, the levels that they're producing. And what I want you to notice here is, so this is the true color, and you can obviously see the plume, but you don't really see a point like a flame point. Here's the color infrared image, and zoomed out, you don't really see it, but once you zoom in, you can actually see the point of those flames. And then here are the DSIS spectra below, and you can see the spectra for the surrounding landscape, and then the spectra of the fire. And then here's another with just the spectra of the fire. And the key here is the dynamic range of DSIS is large enough to be able to study the surrounding area as well as has enough bit depth so that it can capture the strength of the fire that's happening there. One of the things I do want to comment on here, we've collected a number of images for the Australian bushfires. I have not had a chance to look at the super smoky ones. I'm a little pessimistic on being able to penetrate smoke with the bands of 400 nanometers to 1,000. It's typically the shorter infrared where you can really get into the thicker smoke plumes and detect fires. But if you have thinner veneers of smoke, you can definitely see through them with those bands, as well as use this type of imagery for air quality to threshold some of the shorter wavelengths to look at aerosols. The vegetation and food security, I could go on. In fact, I did like a 4-hour seminar on vegetation analysis and hyperspectral imaging. It's a deep topic. It's a complex topic because think about vegetation. If you have an oak tree, and it's fall, you're going to have green leaves, red leaves, yellow leaves, but they're all oak leaves. So vegetation can look very different within a tree, within a field, and it can be very complex to study. And there's actually some really interesting work being done by the USGS, Prasad Sankabale, and his GISA program with very large vegetation spectral library. I would encourage you to take a look at that. I'm extremely excited about the work that he's doing because I think it's a good way to potentially solve some of the variation in vegetation. But 30-meter resolution is effective more for regional area analysis. You can do crop and field analysis, but you're not necessarily, if you're working with a tiny field, it's not necessarily the resolution that might be too coarse for the kind of analysis with very tiny fields. Hyperspectral data is sensitive to various different kinds of vegetation pigments. So you can see this is DISA spectra actually of the Kanza prairie area. And you have pigment absorptions here. Here you have chlorophyll. So you have your pigments here and here. So you've got your carotenoids and xanthophylls. You have your anthocyanins. You have chlorophyll reflectance here. You know, chlorophyll is obviously, that's why plants are green, is chlorophyll reflectance. You have your red edge, which is where leaf structure starts to come into play and how turgid the leaf is in holding water. So there are different vegetation indices to study those pigments and how prominent they are. And those can tell a lot about the condition of the plants that you're working with. This image here on the right is showing different leaf phenotype of nitrogen absorption. So this is high nitrogen uptake. You have low nitrogen uptake and high nitrogen uptake. And you can see how, visibly they look very different. And even in the near infrared, you're going to see a very different signal as well from those. So one of the things about vegetation, in addition to, being able to studying it esoterically and better understand vegetation signals, is that stress over time can create food insecurity. And that can lead to geopolitical instability. So being able to study vegetation over time, especially in areas of the world that may be undergoing geopolitical change or challenges, and understanding what is their wheat supply, what is their corn supply, and understanding their harvest is key to being able to predict any geopolitical problems, struggles, work with the Defense Department, or highlight an area that might be at risk for falling into conflict because of access to food. And then agricultural companies can, of course, use this information of these subtle pigments to study the efficacy of their treatments. So organizations that are creating and testing new fertilizers, new weed and pest control, in order to say that they provide X advantage or X improvement, would be able to take this kind of data from DSIS and use that to exactly say, adding this fertilizer caused an increase in this pigment or a decrease in this pigment, and that was, not good. So let's get on to our last example, and this is also a near and dear one, rare earth elements. So most geologic features, for those of you in the hyperspectral world, know that they are found in the shortwave infrared, and this has to do more with mineral structure. But as I learned this year, I did not know this before, rare earth elements, or REEs, the absorption is due to crystal field transitions involving deep line electrons. And I did not make that sentence up. It's on the USGS site, and you can read a lot more about how rare earth elements reflect in the visible and near infrared there. Currently, China is a primary source of rare earth elements, but because of cost and international sourcing, that may potentially change. So there's the opportunity to look at rare earth tailing piles from mines that are closed, to investigate how much is available in open pit mines, and basically detect the presence of these materials and whether it's economically sustainable to look at retrieving these materials. So USGS scientists were able to take DSIS data and confirm and delineate two versions of rare earth elements present in the 2.55 nanometer DSIS data, and that was basanite and hydrobasanite. And those were basically separated by a hydroxyl group. So it gives you a good idea on the subtle differences that DSIS is able to provide here. And this is really due to the high signal to noise that DESIS is able to provide. So you can see the spectral signatures here. And then this is the Ivanpah Playa, the mine that we're taking that from is here. And here's a zoom in. And this is courtesy of the USGS. So the value of hyperspectral for rare earth elements. So using these resampling tools, we can see that the absorption features that define the REs disappear. So again, we can see here, this is the 2.55 nanometer in the red. This is the resampled 10 nanometer, and you can still see the absorption features in both of those DESIS products. However, when I resample the data either to WorldView 2 or Landsat, you can see that essentially those features completely disappear. So we believe that, to quote Dr. Swayze from the USGS Spec Lab, this may be the first demonstration of rare earth element detection from space. It may also have high enough signal to noise, have enough resolution and signal to noise ratio to allow differentiation of individual RE minerals. Because of that, because of the DESIS quality, this application is potentially a reality. So I'm really excited about, we've imaged some other mines throughout the world. I have not had a chance to look at all the data yet that we've gotten, but I'm very excited about this application. So that concludes our case study. So now I'm going to get into actually getting DESIS data. And there's a couple of caveats. The Teledyne Brown catalog can be browsed as a guest, and the address is there. You will be receiving the slide deck, so you can pull that out, but it's teledyne.tcloud.host, fairly intuitive to search. You can see some of our U.S. coverage here, and you can see some of the longer strips that we've collected. Catalog data is freely available to U.S. federal research scientists via our NASA cooperative agreement. Yvonne Ivy is the POC for this catalog access, and her email is embedded in this. So if you meet those qualifications, please reach out to Yvonne. You can reach out to me as well, and she will provide you catalog access to the DESIS data, a login to be able to self-service. DESIS will eventually be available at the NASA Earth Data SmallSat Data Buy program. And you can read about that. They're doing some phenomenal things. They've got planet data already there. Spire will go up there, and potentially some other sensors. But it's a great program. It will be, the DESIS data will initially be restricted to U.S. government workers, but we're seeing how that evolves at this point. But that will be probably available, my guess is in April. Academic and non-governmental organizations, nonprofits, small data needs, like several scenes, please contact the DLR, so the Deutsches Zentrum für Luftraumfahrt. They have a short proposal process for obtaining data sets. So they can help you access the data, order it, and get started. And then commercial, academic, NGO site access, technical questions can come to me, and my address is embedded there. And when I say site access, so like we have an agreement with the Alabama Remote Sensing Consortium, and that includes multiple schools across the state of Alabama. And we have agreements for certain volume of data that they can draw on. So if you have a university statewide system and would like to get access, I'm the person that you would talk to. And just a little bit of fine print. So we've talked about DESIS being 2.5 nanometer resolution. That is available only to the U.S. government and the DLR. Large commercial or site access may be eligible for a NASA waiver or, a NOAA waiver, but that would be on a case-by-case basis. So the data you would be receiving is typically going to be our 10 nanometer data, which quite frankly has higher signal to noise. It is still very, very nice data. But if you absolutely need the 2.55 nanometer data, we can potentially negotiate that. So to conclude, what I've been saying, it seems like every day is every pixel can tell a story. So the images here that are on the right, actually our marketing, one of our marketing coordinators prompted me on this on International Penguin Day and discovered we had some Falkland Island images, and there's rockhopper penguin colonies there, and started just poking around with the data, and we were able to find little paths, and we think what we see is a beach, a beach colony, and we'd love to have somebody send us to do the field work there to study and confirm that. But when I'm looking at this image, I see there's all this nutrient-rich water. I want to see this image over time so I can see how that colony is evolving and changing. Is it reacting to climate change? I think that there's so much that can be learned from each one of these data sets that it's simply blowing my mind. And you almost have to use big data techniques to really get your head around these, because otherwise you can interrogate a pixel for days. And I try not to do that too often. So, I encourage you to get creative on what you can do with this kind of data, because we're getting hyperspectral data in places that have never seen it in this world. And it's allowing me personally and the researchers who are getting this data to ask questions that they didn't think were possible. So I'm extraordinarily excited by this mission. Like I said, I've been in hyperspectral for a long time. I've worked with a lot of different hyperspectral sensors, and I've never had so much fun as working with, the high quality data that I've been seeing here. So for those of you who are interested, Teledyne Brown Engineering will make a DESIS sample image available. So please send me, Amanda, your contact information. I need that to approve you to get the data. There is that bullet point there on DESIS CalVal information. So for those of you who are pretty techie, that is an exquisite document of how we got to getting data at this quality. And if you're interested in trying this in NV, please contact geospatialinfo@l3harris.com. So thank you so much, Megan.
Thank you, Amanda. At this point, we will address a couple of questions. We are cutting it a bit close, but don't worry. If we don't get to your questions, we will answer them offline. And if you have any more questions, please put them in the question dashboard. Amanda, I was able to find a couple for you that we can go over.
Okay.
The first one is, what did you mean by resampling to Worldview 2?
What did I mean by resampling to Worldview 2? So NV has a capability in it to resample spectra to other sensors. So I took the hyperspectral data and I used the NV resampling tools in the Spectral toolbox to basically convolve the hyperspectral data into Worldview 2 bands. So I can compare what the signature would look like at Worldview 2 resolution versus at DESIS resolution.
Thank you. Let's see. How about, can I combine DESIS with other shortwave infrared hyperspectral data like AVRIS?
You can potentially do that. I would encourage you, if you're working with any AVRIS next-gen program, either out of JPL or NEON, to try to coordinate underflights with DESIS, so we'd at least collect on the same day, but then you would need to do some spatial resampling to combine it to meet the spatial resolution and the slightly different spectral resolution of the AVRIS next-gen, but it's something that we can certainly talk through.
Good to know. You talked briefly about the atmospheric correction over water. What would you use over land?
Over land, because I'm an NV person, I use the atmospheric correction toolkit. And I personally use Quack because it is fast and easy, and I generally get very nice results. You could also use Flash as an unknown sensor, and the sensor parameters are mostly contained within that calibration document or an FAQ that's on the Teledyne webpage. But I personally use Quack. I haven't used other tools, but it's the NV atmospheric correction toolkit.
Fantastic. I'm looking for, I think we'll do one more question.
Can we just address the training? So,
absolutely.
Certainly if you really just want to learn about DESIS data, give me a call and we can talk about potentially doing some over-the-shoulder work. And then Harris
also does classes. We have a big hyperspectral background, and so we do trainings as well, specifically on focusing on learning, analysis, and getting results you need from hyperspectral data. So please feel free to reach out to me or to the email that was on the previous slide. All right. With that, down here. So with that, we are going to wrap things up. If we haven't gotten to your question, we'll answer those because a bunch of them just came in, and so we'll do our best to answer them all. We appreciate everyone's attention on the line, and thank you again, Amanda.
Thank you. Thank you for the invite to let me blabber about one of my favorite topics.
No, it's great. I love the penguin the most, though.
It's fun.
So just a reminder that this has been recorded, and this webinar and the slides will be emailed to you in the next couple of days, as well as with a couple of more handouts on information. It will also be available on our site at harrisgeospatial.com, and we encourage you to share it with all of your colleagues. Thank you, everyone, and have a great rest of your day.